Hello everyone, my name is Dharamveer Kumar. I'm a PhD student at IIT Bombay, and today I'll be solving assignment 9. Okay. Uh, so till now I hope everyone has understood what I've been telling. Okay. Just one second. Use the fan. It's red. So I'm in Mumbai right now. It's very hot and humid over here. Just one second. Okay. I'm just waiting for few more people to join, and then I will get started. One second. So assignment 9, right? Let's see. Yeah, so assignment 9. So let me once check if the recording is proper or not. Okay. Just let me check because there have been issues in the past. Yeah, hello. Yeah, so my video was gone for like 5 minutes. So what I was telling you, I just wrote down the question that f is from r square to r defined as this, and I wrote down all these options that f has exactly one point of local minima and one point of global minima, right? What does it mean? In one dimension, if you want to understand, something like this. It is exactly one point of local minima, no other points are local minima. Okay, and this is also a global minima. Can we have one local and multiple global? But so when you're talking about open space, right, on R, like R square is an open space, right? All global are local, not the other way around, but all global. If there is a global minima, that's definitely a local. So I'm not talking about infimum or something like that. I'm not talking about a case like this, something like this. It will reach at some point. No, not that. The global minimum is not at what happens at infinity because it's not closed. So when you have a closed set, right, a compact set, something like this, these points are counted. So what is the global minima? It is the infimum of, or rather minimum of all local minima and endpoints. Okay, a function inside this can have multiple local minimas. Okay, so what to do in that case? Like it could have a countable. Can it have countable? Yeah, it can have countable local minimas. Okay, so okay, so this is the definition when finite local minimas are there. So this is what a global minimum is. It has to be one of the local minima or endpoints. But let's say if something is not an endpoint, there is no endpoint in open space R, or like there are no endpoints, something like this. Okay, and you want to find what a minimum is. Okay, the minimum should exist. Let's say local minimums exist. So a global minimum will definitely be a local minimum, because let's say there is any point, right? It's an open set, so there is a ball around it, right? So there is a, let's say pick any point, and let's say you're claiming that to be a global minimum, right? You have a open set around it, right? And if it is not a minimum in that open set, it cannot be minimum in the whole space, right? So what global minimum means, that local minimum means there exists a open set around one point, so that it's minimum in that. So that implies all global are local in open sets. Okay, just because there was a something wrong with the recording, I just need to check once more. Okay, so I think we're smooth now, everything is working fine. So this you should keep in mind, all global are definitely local. So if that's why there is no option that F has one local minima and more global minima, that cannot happen. Okay, what about B? F has more than one point of local minima and exactly one global minima. Yeah, that can happen. A simple example of something like this, and then going to infinity, right? This has 1, 2, 3 local minimas and one global, so that can happen. But it cannot happen that it cannot happen that you have one local minima and multiple global minima. That is not possible in an open set. Okay, because in closed set, what can happen is, let's say you have a local minima, and at the end it can go and touch this. This is not a local minima because it's not an open set, it's at the endpoint, so it's not local minima. So something like this. So there can be two global minima. Okay, so keep in mind on an open set. Open set is key. F has exactly one point of local minimum, no point of global minimum. How do we draw that? So, hello, are you saying something, Uma? Okay. So, something like this, right? And then going to infinity. A mountain, this is a function. Again, this function can have, this is one local minima and there is no global minimum. That is also possible, right? I'm just trying to see what are the possibility, like do you understand what the options are? This is in one dimension, okay? I'm just giving you a feel of what it means. F has more than one point of local minima and no point of global minima. Yeah, I can draw true, something like this. Two local minima and no global minima. It cannot be more than, it can be less than. So basically the number of global minima will be definitely less than number of local minima in an open set. Okay, or in closed set. We saw what happens in a closed set. So you need to keep all these things in mind. Okay, so let's see. The first question is there is no constraint or anything. Okay, so this is assignment 9. So now let's start with how we usually solve it. Okay, so let's find what fx is. This is the derivative with respect to x. This is nothing but 2x for x square. It's a partial derivative, all the y terms will go to 0, and then minus 2. What about fy? It is as well 2x minus 6. When is this 0? So fx is 0 for all x equal to 1. When is this 0? For all y equal to 3. So basically fx of, this is a necessary condition, we are talking about local minima right now. So for if there's something is a local minima and the function is differentiable, this will do we need both the derivatives to be 0? Okay. We need both the derivatives should be 0, right? So that implies, okay, 1 comma 3 is only critical point. Okay, so you cannot have more than one local minimum. Now if there is a global minimum or not, that we need to find out. Okay, and if this is a minimum or not, but there are two options. In both it says exactly 1, so I think it is exactly 1. We don't need to check it, but I will do it for general purposes to find out what exactly it is. Okay, so what you do is fxy this is fx. Okay, so if you do, you get 2 comma 2 0 0. Okay, and you take the determinant of that. What is that? 4, which is greater than 0. Okay, and fxx is greater than 0. That implies minima. Okay, so what it says is the fxx is greater than 0. Okay, so if you want to look at this, this is called like a Hessian criteria. Okay, so what do we do now? The Hessian is positive. 1 second, there are more people who want to join. Admit. Whenever you have any questions, you can just ask me, okay? If you're not understanding something, okay? That implies 1 comma 3 is the local minimum. Okay, so if you look at it, it says positive definite. Okay, Just 1 second. Let me just write it down. There's a whole list. I don't remember it. Okay, yeah. So I will just write down the list of everything. Okay. So if those points are critical point, okay. So determinant D is determinant. This is maximum. D is greater than 0 and fxx x star y star is greater than 0, then minimum. If D is negative, saddle point. If D is 0, inconclusive. Okay? And D is amount of, just remember this about the minimum. It's a local minimum. Now, does it have, is it a global minimum? That's the question, right? Is it something like this? Or it cannot even go to infinity, like something like this. Okay, converging to some value, converging to different values. Okay. So the question is either it has one point of global minimum or no point of global minimum. So it can have only two there because there is exactly one local minimum, right? So it can be 1 or 0. It cannot be 2, as I told you, right? So now what is the case? How do we decide that? Okay, we know at 1, 3 it is a local minimum. There is exactly one critical point. So we also know there is exactly one critical point. So if we were dealing in one dimension, it doesn't have a maximum anywhere. It doesn't have a local maximum. Note, neither does it have saddle point, or so we cannot encounter case like this. Because if there is some point which is a local minimum and one point whenever it is outside this, it's continuous, right? So you can apply rule of continuity. So let's say this is r square, right? We're defining a function on this, right? And let's say there is another point. So either it can grow from there. Okay, this is the minimum. If there is a point, any point which is lower than this. So let's say this is 1, 3. And let's say there is x star, assume, or rather we'll just call xy, assume mn basically. such that f of mn is less than equal to f of 1 comma 3. Okay, assume either it does exist or it doesn't exist. Okay, I'm also given equality, so assume that something like this is happening. Okay, so there is mn and there is 1 comma 3. What you do, you draw something like this, a circle, or rather just take a double point and draw something like full circle, something more than this. So basically draw a compact set, draw a compact circle, disk basically, containing f is continuous. We don't need to prove it, it's just sum of polynomials. It is continuous, not an issue. That implies f has a minimum, it's a continuous function, undifferentiable if a function, so that implies mn has to be in an open set, as I said, right? If it in an open set, okay, there is an open set, and we know that there are finite number of local minima. That is exactly one local minimum. In that case, a global minima is nothing but definitely a local minimum. M has to be local minimum, but hence this is how you have to prove. Hence 1 comma 3 is the global minimum. And then okay, this is correct, this is wrong. Okay, let's go to question 2. So once we have sorted this out, like once everything is done, it's easier to do the rest. So now f from r square to r, we have already given, I've given all the conditions, right? Let's see. So f from r to r, we define as 4 plus y to the power 4 minus 4xy plus 1 for all xy in r square. So now it's a true and false question. The origin is the saddle point. In order to check this, first see when is fx. So what is fx? 4x cube minus 4y. And what is fy? 4y cube minus 4x. You don't need to find out all critical points. Easy to see. At 0, 0, fx of 0, 0 is 0 and fy of 0, 0 is 0. That implies origin is the critical point. What is fxx? 4 12x squared this is 0. What is fxy? Minus 4. What is fyx? Minus 4. What is fyy? 12y squared. Okay, so what is the determinant? At 0 0, it is 0 minus 4 minus 4 is 0. Determinant at origin is nothing but minus 60. So let's look at the condition. Determinant is negative. We are done. We don't need to check what fxx and stuff like that are. Determinant is negative. Saddle point. That's it. As simple as that. Have you seen a simpler problem than this? Okay. Let's do question 3. Before that, there are numericals. These are numerics question. I'll come back to those later, where there are like numbers. Numbers we should do later. Everything is a number only from now on. Okay. This question 3. If a rectangular box without lid. So a rectangular box without lid is to be made with 12 meter square cardboard, and what is the maximum volume of the box? So there is a cardboard, so it's a length be AB, and A into B is 12. So you have to do, what you have to do is, all you have to do is fold it. That's it. You cannot cut it and everything, just you have to fold this. Okay, there's a cardboard, you need to like fold it like this. So something like this. If I have B, if I can take X length from here and I fold it, right? Yeah. Give me a second. Let's see what it means. Yeah, no, I don't think so. Yeah, you don't have to fold it. It's just AB is equal to 12, and let's say there is a length called, there is X, there is Y, there is Z, right? And it has to be made from here. So you have to maximize what? X, Y, Z, max of X, Y, Z. Okay. X is greater than 0, because this whatever, it cannot be 0. X, Y, Z greater than 0. So that's how you have to maximize. But there is a limitation that the area of this cardboard is same as 12. Okay, so that means constraint. What is the constraint? That this ZY is 2 times, right? There are only 5 surfaces. 2 times ZX and only 1 times XY. And you have to maximize this. Okay, and this is equal to 12. So we are not wasting any code. However you want to do, doesn't matter. So what do we do in this case? What we do? We are not putting this constraint up. It will automatically come out. Okay, we'll see how. So xyz plus lambda 2zy 2zx plus xy minus 12. Okay, we write this j of x, y, z and lambda. So what you do is dou j by dou x first. That is yz plus 2z lambda plus lambda y. With y lambda 2z plus lambda x. Dou j by dou z is equal to xy plus 2 lambda y plus 2 lambda x, and all are 0. So now this is a four variable and with d lambda, and then there is a constraint for sure, right? Four equation, four variable. You can solve this. First try to solve this, everything in terms of lambda, then we'll substitute and then we'll get lambda. Okay, so how do we do it? So yz plus 2z plus y is equal to, oh sorry, because lambda is minus yz by 2z plus y is equal to okay, leave everything. There is yz, xz and xy. So from these two equations, from first two, what is common in there? Z. Let's eliminate z. Okay, how do we eliminate z? So first we write z equal to minus lambda y over y plus 2 lambda. Okay, that implies minus lambda xy over y plus 2 lambda, it is xz, plus 2 lambda into minus lambda y y plus 2 lambda plus lambda x is equal to 0. And then we also have xy over here, and xy plus 2 lambda y plus 2 lambda x is equal to 0. Okay, now it's the easier method to do this. One second, let me see. Oh, okay. There is an easier way to do this. By intuition, if you look at this, right, only z will have to change, because what is the height we are giving? Because when we are multiplying it over here, right, x and y are same. So by symmetry also you can take x is equal to y. Always you can do this in general. You'll have to, I'll show you why it is the same. But you can do this by symmetry as well. Okay. This implies lambda is equal to minus yz over 2z plus y. Okay, lambda is equal to minus xz over 2z plus x. And this implies lambda is equal to minus xy over 2 times x plus y. If we substitute these, we use this, okay, and z is not equal to 0. This is gone. That implies minus xy minus 2zy is equal to minus x 2z minus xy. Okay, minus xy is gone, 2z is gone, that implies x equal to y. Okay, z was gone, minus 2zy minus xy minus 2xz minus xy, this is gone, and we subtracted minus 2z, it implies x equal to y. That's what I was telling you. Once you do x equal to y, okay, we have compared these two equations. That implies, now let's do with z, okay, and so basically minus xz over 2z plus x is equal to, instead of y just write x, minus x square 4x. Okay, so minus x gone, minus x gone, there is x, there is x gone. That implies z is equal to 2z plus x by 4. That implies z by 2 is equal to x. X equal to y equal to 2z. What about lambda? Lambda is equal to and then there is a constraint over here, right? 2zx. So if you want to put z in terms of x, okay, 2 into x by 2 into x plus 2 into x by 2 into x plus x square is equal to 12, right? 3x square is equal to 12. 4. I told you, right? X positive negative will come into picture. That implies x is equal to 2, y is equal to 2, and z equal to 1. From here, you will be tempted to just write x is equal to 4. Okay, and that is the maximum volume in the option. Okay, it's achieving 4. Definitely there is no maximum that you can just write it, right? But it may just be a low, how do you say, a local minimum, right? Basically, we are finding the critical point of this Lagrange. That critical point corresponds to the local minimums in the original solution. It could be a local minimum, right? Or it could be a maximum. We don't know what it is. It is minimum, maximum, nothing is known. Okay, but based on options over here, sometimes it's hard to find. You have to do double derivative test and everything. That is a little harder to do in general. So what you do, you find a critical point, and this is a critical point for sure, right? It is the critical point in our equation. It is a critical point of, but it is a maximum or a minimum. It's a global maximum, global minimum. We don't know that. Okay, we don't know that. There is a volume. I can take x or one size to be as small as possible, and still this will be 12, because the 12 can come from these two, x, y. Z can be as small as possible, doesn't matter, almost tending to 0, very inconsequential, and x, y will be something. Okay, so I can make it as small as possible, as close to 0 as possible. Okay, so in that sense you have to understand that whatever the critical point is not a minimum for sure, because I can make it as small as possible. There is no minimum. The minimum is 0. So the solution is maximum. I've not shown that it is a maximum. No, that based on options. Because we are achieving 4. We cannot do anything more than that. Okay? Double integral of the function over the domain. Double integral again. I'll skip the double integral, and I'll first do the maximum and a minimum questions. Okay? Since we are on that flow, I'll do that. Okay? Okay, question 6. Consider a function from r square to r. Let it define as this is a very simple question. Set of all critical points. You have to find all the critical points. That's it. Simple, easy peasy. Okay. Hey, has anyone asked any question or something? Okay. So here's the solution. Fx. partial derivative with respect to x. So what am I first supposed to do? Differentiate with respect to this chain rule, right? So y e to the power minus square minus y square plus xy that implies this term is never zero except at infinities, right? You need a critical point inside. So this term is never zero. No matter what xy put, this is always positive. So when it is zero, it's on these points. What is fy? They are the same, as you can see. They're symmetrical. So whenever something is symmetrical, everything happens, anything interesting that happens is on similar points. Okay? So I can just substitute xy and stuff like that. Okay. So now fx equal to 0 when y is equal to 0 for any x, and when y is not equal to 0. So when y is equal to 0 for any x, when y is not equal to 0, when x is plus minus 1 by 2. Similarly, f of y is equal to 0 when x is equal to 0 for any y, and when x is not equal to 0, 1 minus 2y square is equal to 0 implies y is equal to plus minus 1 by 2. So when is this common? So x is equal to 0 equal to fy. So fx is equal to 0 when x is equal to 0 at any point in y, right? So from this case, it's 0 comma a, the whole so when y is equal to 0, we'll not have this case, right? When y is equal to plus minus 1. When y is equal to 0, only this coincides. That implies 0 comma 0. That's it. And then in another case, let's y not equal to 0, but x is this. What about this case? Not possible, right? So only this pairs. When x is equal to, it could be anything, okay? It could be anything, 1 minus root 2 to plus 1 root 2 plus 1 by root 2, and then minus 1 by root 2 with plus minus 1 by root 2. Yeah. So with plus minus, with minus, plus minus. With the plus minus minus, so plus minus 4 times. One, two, you can write it in any way, basically option A, okay? Now question 7. Okay. Consider a reason r squared r defined as fxy is equal to xy square for all xy and r square. Okay, and the region D is such that x is greater than equal to 0, y is greater than equal to 0, the first quadrant, and x square plus y square less than equal to 3. Maximum and minimum of FR. This function is nice, continuous, differentiable, everything, right? Very simple function. Let's plot the D area, right? It's the first quadrant and x square plus y inside 3. So it is with something like this is closed and bounded compact set. So F has a minimum and a maximum. So we have to check the boundary in the open set inside. Okay. So now let's see where fx is equal to 0. So fx is nothing but y square, and it is 0 for all y is equal to 0. What about fy? So y, what do you mean by y equal to 0? This line, right? And you have to be inside this. So it's saying this line is a critical point for, like, not a critical point, fx is equal to 0 on this line. What about fy? It is 2xy. So when can this be 0? So x is equal to 0, y not 0, x equal to 0, y equal to 0, x not equal to 0, y 0. So this point, this line, okay, including this point and this point. So this is the critical point. This is the critical reason. But when we have a bounded, closed, compact bounded set, we are looking for a global maximum or a minimum or anything, we have to check. So what happens when y is equal to 0? This line, the f is 0 over that point. So f on critical line is equal to 0. This is the critical line, and over there it is 0. So, and definitely if you can take any positive function, it will be positive. So that implies but xy square is always positive. That implies minimum is 0 and there is no local maxima, hence max lies on the boundary. What about this boundary? F is equal to 0 over here. What about this point? What is this boundary? X square plus y square equal to 3. what we can do is that implies fxy on non-zero boundary is nothing but, so there was x into y square, and y square is nothing but x into 3 minus x square. Okay, what is this equation? 3x minus x cube. It's a single equation you have to find on this line where the maximum is. Okay, what do you do? 3 minus 3x square equal to 0. That implies x is equal to plus minus 1. Since x is greater than equal to 0, x is equal to 1. At x is equal to 1, there is a critical point. Only at x is equal to 1, there is one critical point. This function on this line, if you are looking at a line, it's a single variable, it's 0 at some point at the boundaries. Okay, if you look at this point, at x is equal to 0, or y equal to 0, right? It's actually x into y square. Either x is equal to 0 or y is equal to 0, it is 0. So, so basically x in, where we have to look at for x in 0 to root 3, closed. And in both the cases, so basically now if you want to plot this, at 0 it is 0, and root 3 it's 0. Okay, at other places it's definitely positive. What it is we don't know, and there is a something locally happening. Okay, this is only 0 at these points, and the function is always positive, and something is happening critically. There's one, so you cannot have something like this, because there is only at x is equal to 1 something is happening. So its function is something like this if you want to plot this. So basically at x is equal to 1 something happens, so x is equal to 1, and what is corresponding y? X equal to 1, it will go 2, y will be root 2. So f of 1 comma root 2 is what? 2. This is the maximum. You have to think like this. You have to like plot and do something like this, because it's not a simple thing to just maxima and minima, like second Hessian test. We're not dealing with the open set anymore. Okay? Question 8. Last year this was wrong, basically. Last year it was written find the maximum value. Actually there will be a minimum value. So let me write it down. The solution. Trivial, right? Very trivial. And so what you can do, x is lambda by 2, y is lambda by 2, so that these implies y is equal to z is equal to lambda by 2. So if you substitute that over here, and that implies 3 lambda by 2 is equal to 12. 4. So if you do, basically if you do f x y z, it will be nothing but 4 square into 3, that is 48. Is it a maxima or a minima? For instance, take x is equal to 1, y is equal to 1, and z is equal to 10. So then it is a minima, not a maxima. Okay, it was the error. It is not a minima because we already find a point greater than this. Okay, I hope you understand this. There are other ways to solve this problem. Okay, what you can do is x plus y plus z square is equal to x square plus y square plus z square plus 2xy plus yz plus z. I don't think you can do that. Yeah, like this is how I'm just giving you an example why it is a minima, not a maxima for sure. What is this physically? What we are saying is it's a sphere okay, we are drawing a sphere subject to a plane. Okay, you have to understand it like that, and you will get a gist of it. But this is how, so you don't do double derivatives in this case. All you do is deal with single derivative and things are good. Take a break here. Yeah, so we'll take a break here and then we have to do one couple of questions about integration. Question number 4, 5 and 9. Let me see those 4, 5 and 9. Okay, yeah, let me take a break and then see you in a few minutes. Okay, so I'm back. Let's do question 4. It's a simple double integration. Okay. This is the function over what does it mean? Let's draw the domain. In X, it's from 0 to 2. It's a rectangular, nice domain. In Y, it is from 1 to 2. And this is the domain. There is no cross terms or anything. It's a nice domain. We can like do a simple integration, which is x minus 3y square dx dy x from 0 to x to 2 y is equal to 2. Let's first do with x. Okay, nothing but x square by 2 minus 3y square x, right? And you can put the limits. You put before and after, doesn't matter, but just doing it because you don't have to deal with numerics again and again. So x is equal to 0, this is gone. X is equal to 2, it is 2 minus 3y, 6y square. So you kept y equal to constant and you integrated this line. Okay, so for y is equal to constant, you are integrating x minus something. So you're not integrating like area under the curve. We're integrating. It's a 2D function. On this line you have integrated. Now after this you have to integrate with I is equal to it implies I equal to, this is nothing but 2y minus 6y cube over 3 from y equal to 1 to y equal to 2. So this is nothing but 2 minus 2 of 2 cube minus 1. Option D. Simple, right? Question number 5. Similar question. Integrate xy is equal to y sin xy over. Now over here earlier there was not an issue, right? Both were polynomials, you can easily integrate. Over here you have to choose. With y it's harder to integrate, y sin y, but with x it's easier to integrate. I'll show you. The solution is equal to y sin xy. You can integrate in any direction because it's a nice simple rectangular integration. Function is continuous, everything is nice. It's a finite domain. X is from 1 to 2 and so is equal to that. first let's get rid of x. Sorry, anyway. This region. Okay. It's nice to draw regions when you're dealing with, make it a habit for complex integrations. Dx, first with dx, then with dy. Okay. What is with dx? How do you integrate sine xy? Okay. You want to integrate this and x is a constant. What you can do is, right? Hello. Oh, the network was gone now. So what you can do is simply just, how do you deal with this? How do you, just normal definite integral, how do you deal with this? What you do is, you take z is equal to tx, okay? So then dz is t dx. T dx is nothing but dz, and this is sine z. And then what you get is minus cos z. Similarly, that implies I is equal to and then substitute minus cos dx. So minus cos xy with x is equal to 1 and x is equal to 2. Okay, x equal to 1 is minus cos, so x is equal to so for it's the second variable, so there will be a minus sign, so it will become cos y minus cos 2y. Okay, and you have to integrate this. Cos y is nothing but sin y, and minus 2 cos y is nothing but sin 2y over 2. From y is equal to 0 to pi. At both 0 and pi, for all values, this term is nothing but 0. Okay. Let's try to do this from the other way around. Let's try to first integrate with y. You want to try? It will be very difficult. What is the integration of, like, let's say, if you want to integrate, how to integrate t sin t dt? There is a website called Wolfram Alpha. It gives you a very nice integral, very simply, right? So I just wanted to tell you that you can just do things over there. Integrate t sin t. Sin t minus t cos t. Sin t minus t cos t. That is the definite integral, okay? So if you want to calculate this, right? So alternate way. First you have to borrow this. It's hard to prove this. Okay? It's not hard, but means it's not a direct functional, like you have not used any trickery over here, just simple sine integral. Okay, so when you do this, okay, what you encounter is, so you have to like from 1 to 2, there is dx, and then there is dy over here, right? So you have to multiply with x first, and then you can use this. This implies dx over x from x equal to 1 to 2, and this thing, again with change of variables, what you can do is it's nothing but sine xy minus xy cos xy, and you have to put y is equal to 0 to pi. This term will vanish. This term will vanish for 0. What happens at pi? That implies I is equal to dx over x into minus x pi cos x pi from 1 to 2. So x will get cancelled, right? So this will be just minus d of x pi cos of x pi from 1 to 2. This will be minus of sine of x pi from 1 to 2, and then it will be 0. So if the limit of integration were not easy, it would have been over here. The limit of integration doesn't matter because we are getting 0 only at the end. So as you can see, this part more difficult. So you always have to choose the easier one. Okay, this is the easier part, and do this when you are integrating. Okay. Now 9th question. It's a true and false question that 0, if we take double integration, over this R region, it's a region of sine pi x cos pi y dA, double integration, R equal to 0 to 1 by 4 plus 1 by 4 to 1 by 2. You can see this was such an easy class. This is the last question, and we are like half an hour is remaining. Okay. Solution. What is the region first? This region. Okay. This is dA is nothing but dx dy. Okay. So without solving first, let's try to do this without solving first. Okay. So I want to draw one function. Let's draw sine pi x in this region. What is it? X is equal to 1 by 4. This is, the value is sine pi by 4. What is sine pi by 4? 1 by root 2. This is the plot of sine pi x. It's increasing. Okay, it's going from 0 to pi by 4, like how sine goes, in a similar sense. So sine pi x is between 1 by root 2 and 0. That implies sine pi x is this 1 by 4 into 1 by root 2. What about cos pi y? So it's going from pi by 4 to pi by 2. How is the cos curve? At 0 it's 1, pi by 2 is 0. So from pi by 4 to pi by 2, 0 is going from pi by 4, it is also 1 by root 2. So cos pi y is also, it's a decreasing function, it's also, but still this is the case. That implies cos pi y from 1 by 2 to 1 by 4 is positive, but again bounded by 1 by root 2 dy from 1 by 2 to 1 by 4, which is nothing but 1 by 2 into 1 by root 2. That implies I is equal to 1 by 4 bounded by 1 by 2 into 1 by root 2 . Oh sorry, it is 1 by 4 over here. We are not doing any calculation, we are not evaluating root 2. Just imagine in a world where we don't know how to evaluate root 2. We don't know the value, we don't have to do anything. This is the very easier way, without even doing calculation. Like obviously you can do something like this, right? Easily 1 by 4 to 1 by 2. Then when you evaluate this will be nothing but turn it down, minus cos pi x from 0 to 1 by 4 and times sin pi y pi from 1 by 4 to 1 by 2, right? What is cos? So this will be minus cos pi by 4 minus plus cos 0 by pi. This multiplied with sin pi by 2 minus sin pi by 4 divided by pi. This is nothing but cos 0 is what? 1. 1 minus 1 by root 2. And this is also 1 minus 1 by root 2 square over pi square. How do you evaluate this? How do you know what is greater than or less than or something like that? Basically 1 by 32. Okay, the value is, see, if you want to calculate the value, This is roughly around 0.00869. Okay, you can say that yeah, this is less than 0.03, but when you're going inside zero, right, it's harder to evaluate these things. Okay, okay, so like let's say for example, for instance, why it is very difficult. If you do something like this, right, if you estimate up to 1 decimal places, if you only take 2 decimal places, this is 0.09. Which is definitely greater than this. But if you take something like this, so if you like approximate this and then you take a square, you will get 0.0081, something like that. But you have to do this calculation. What we got over here is without doing any calculations. So you have to aim to do something like that. Okay. Now I'll tell you what a Lagrange multiplier is. I'll give you an explanation. Before that, do you have any questions? Kartika, is there any question? Any week, yeah, just any questions, just yeah, yeah. It is defined for any real number p greater than 1, greater than equal to 1. For infinity, it's a special case. I don't understand what. Okay, just tell me. Yeah, just I can go through that. Yeah. Sorry. Week 11 assignment. Yeah. Which question? Tell me. The question number 1, right? Yeah. Okay. So, what is a norm? Do you understand that it's a function? Okay. So, if there is a function, if the function satisfies certain property, it's a norm. Yeah, there are 3 conditions when it satisfies, it's a norm. So it's what is norm? So if you have a vector, right? You understand vector. So it takes two vector and it gives a real number. It's a function which takes two vectors and gives a real number. Any function okay, it gives a real number. Now it has to satisfy certain properties. This is weird. Also, I'm not advertising for it, but you can also look for step-by-step solution of how at least you will get what the substitution they are taking. Okay, now norm of a vector, right? You can just simply see what it means. It has to have sub-additivity, as in if I take norm doesn't take two, it's an inner product. It takes a vector and gives a real number. What it means, what we have to do is for all x, y in V, f of x plus y will be less than fx plus fy. This is the first property. Okay. Second is for all lambda in real number, f of lambda x should be mod lambda f of x. And then third is for all x in V, f of x is greater than 0 and f of x is equal to 0 if and only if you got this? So if you show all these three, that's a function is defined, okay, and if you show all this, you're done. And why it is so, this condition is already taken in here. If you define something like this, 0 to infinity, so you can remove this and just keep this condition. If you look at it, why p greater than 0 is defined, like you're defining a function, right, for p greater than 0. Many properties won't be defined, like this properties will easily be violated. That's why there's p greater than 0. So first try to find out which option is correct, and then define this for all p, not just p greater than 0, any p, any real number, and then also show that why a specific thing is a norm. Okay. I hope this is clear, right? So I'll go ahead and do one more the idea I wanted to discuss. What exactly goes on in Lagrange multiplier, right? You want to maximize, when you want to minimize, just put a minus sign on it. In one variable, it's very simple. You find a solution where the constraint is satisfied, and on those constraints you define a function. Now assumption is fg have continuous first partial derivative. I'm giving a hand wavy proof. Any proof is hand wavy proof in general in this case, unless they use implicit value theorem and like a lot of things. It's complicated. It's very complicated. It's not easy. Okay. So basically, fx, fy, gx, gy are continuous. What you define is nx by lambda is equal to f of xy plus lambda g of xy. So if x naught y naught maximizes fxy and grad g of this is not equal to 0, then there exists lambda naught such that x naught, y naught, lambda naught is stationary on a critical point of n. Have we used this? We don't use it in general. So there is question 8. Okay, let's go from the beginning. This is a general, there is no constraint. This is also general. Coming from question 3, right? There was this constraint. G of x, y, z basically minus 12. So basically is nothing but, this is nothing but 2zy plus 2zx plus xy minus 12. What do we have to check? That we got this critical point, right? X equal to 2, y equal to 2, z equal to 1. We had to maximize. So is grad g, so if you want to take gradient of g, so now dou g of, or in simple words, g of x. What is g of x? 2z plus y. What is gy? 2z plus x, and what is cz? 2y plus 2x. Substitute these values. X equal to 2 and y equal to 2. Okay? This is non-zero. That implies grad g non-zero at 2 to 1. Right? I think that was the case. it is a maximum. This also we have to, but we are again not saying that it is maximum. All we are saying that, so if a point was a maximum, it would be a critical point. Okay, do you understand this? If a point, what I'm proving is, if there is a point which is a maximum, it is definitely a critical point. But we have exactly one critical point such that this is not. Now, a maximum may exist or may not exist. Okay, but if you look at this with the common sense of what we have, these are positive numbers. Okay, I cannot take x or y to be too high. If any of the product that is included in here, I cannot take it too high. I can take x. If I take x to be too high, y and z have to be too small such that the product is in here. Okay, so that's how we know that there exists a maximum. Now what is that maximum? We find out, but existence is not proved by this method. Similarly, if we go down this road, okay, over here g x y z would be x plus y plus z minus 12. So grad z would be simply 1 1 1, not equal to 0. That's okay. Whatever we get a critical point, if there was a maximum or a minimum, it will be on a critical point. But it does not guarantee that there exists a maximum and a minimum. For that case, there would have been no minimum. Okay, so proof. And that says in other words, plus lambda grad g. Okay, now grad lambda of x naught y naught lambda naught is nothing but grad of x naught y naught plus simple. If there was a critical point, I'm writing just normal lambda plus lambda grad g x naught y naught, right? And we have to find 0, right? So how do we find lambda naught? So lambda naught is nothing but minus grad f So if we do minus and then grad g of x naught y naught, norm square. That is how. So we have to find there exists a lambda naught. If you put lambda naught equal to this will go to 0. If for this we need that grad g of x naught y naught is not equal to 0. So what was this? Okay, so we'll end up with this, and I hope you understood everything, and we'll finish off everything in the next class. I think the time is up. I have to go. Okay. Okay. I'll see you in the next class.